Let's talk about the method of elimination. Last video we did substitution. Now let's try elimination. In elimination, the goal is to eliminate one variable. That's why it's called elimination. Now we'll do that by adding or subtracting the equations together to eliminate one variable. So that's the goal. That's what we're doing. We need to add or subtract the equations together to eliminate one variable. And if needed, we can multiply the equation by a number in order to get things to eliminate. And then once things have eliminated, then we solve. So let's look at the process of elimination. We're adding or subtracting the equations together to eliminate one variable. So if I look at my first example here, I notice that, hey, it's already set up where if I add these equations together, these x's are going to eliminate. They're going to cancel. So I don't have to change anything. I can just use the equations as they are, add these two equations together, and my x's will automatically eliminate. So I don't really need this if needed statement for this problem. I will need it for the next one, however. So I keep adding these together. 4y plus a negative y gives me 3y. And negative 2 plus 5 gives me 3. Solve that to get y equals 1. So same with substitution. I can now use this y equals 1, plug it into any of my equations to solve for x. So I think I'm going to plug it into the top equation. So plugging in my answer of 1. So 3x, 4 times 1 is plus 4 equals negative 2. And then I solve for x. So I get x equals negative 2. And as we did last time, we need to write this as a coordinate point. So x is negative 2, comma y is 1. And because this has a single solution, we call this a consistent independent system. And just like we did last time, I've taken the liberty of graphing these two equations on Desmos so that you can see that this is the point where they cross. So right here, here's my two lines, those two equations. I look at where they cross, negative 2, comma 1. So that point is the point that these two lines have in common. Let's move on to our next example of elimination. Remember, the key is to be able to add or subtract these equations to get one variable to cancel. So if I look right here as these equations are written now, I can't add or subtract to get rid of the x's, and I can't add or subtract to get rid of the y's. So this is where the if needed statement comes in. We can multiply the equations by a number in order to get things to eliminate. So what I'm going to do is I'm going to multiply everything in this equation by a 3, and I'm going to multiply everything in this equation by a negative 2. Now there's a reason I'm doing that. Watch what happens when I do this. So I'm going to start with this one. Multiply everything in this equation by a 3. So 3 times 2x is 6x. 3 times negative 4 is negative 12y. And 3 times 6 is 18. And then I'm going to multiply everything in the bottom equation by a negative 2. So negative 2 times 3x is negative 6x. negative 2 times negative 6y is a positive 12y, and a negative 2 times 9 is a negative 18. Now you can see why I picked to multiply by those numbers, because now I can cancel things out. I can add these two equations and my x's will cancel, and in fact my y's will cancel, and my 18's will cancel. Everything happens to cancel in this one. That does not happen very often. But when it does, we end up with a true statement here. Meaning, yes, 0 does equal 0. Now this true statement could be anything. It could be 5 equals 5. It could be negative 2 equals negative 2. It could be 1/2 equals 1/2. But as long as it is a true statement, as yes, those two things are equal to each other, that means that this system has infinitely many solutions. So if you recall from the first video, we call that a consistent dependent system. There are infinite number of solutions here. And if you take the two equations we started with here and go to Desmos, you can see there's my two equations. My first one and my second one. These two equations are in fact the same line. So because they are the same line, they do have infinitely many points in common. Infinitely many points that they share. Now, that doesn't just mean we can say infinite solutions and be done. There is actually a way to detail the solutions here, because not all points are on these lines. For example, 0, 0, the origin, is not on this line. This line consists of a very specific set of points. For example, 0, negative 1.5 is there. 3, 0 is there. We could see negative 5, negative 4 is there. This is a very specific set of points that is on this line. It's not just all the points, it's a specific set. So let's go back to our answer and talk about how to write that. Now, to write that, we're going to do something a little bit tricky, but you're going to do this throughout the chapter. So if this seems a little weird today, don't worry too much. We're going to do this lots. Anytime we have a consistent dependent system, we're going to start by taking the last letter, and in this case the last letter is y, and we're going to say that last letter is equal to t, specifically. So we're saying the last letter y equals t, and that is my solution for y. Now what I'm going to do is take any of the other equations, so the first one or the second one, and I'm going to substitute t in for y. So let's just take my first equation. And I'm going to put t in for y. And now I'm going to solve for x. So I'm going to add 4t to both sides. 2x equals 4t plus 6. Divide everything by 2, and I get x equals 2t plus 3. And that is my x answer. So now I can still write my answer as a coordinate point, where my y answer is t, and my x answer is 2t plus 3. And this is the set of points that work on this line. So you can take any number you want, plug it in for t, and that's a point on this line. For example, let's plug in 2. So I'm going to plug in 2 for t. And then if I plug that in here, I get 2 times 2 plus 3, which is 7. So 7, 2 should be a point on this line. Let's see. 7, 2. Right there. I can't find it very well. 7, 2. That is a point on this line. So this answer right here is the way of saying all the points on that line that they have in common at the same time. You can take any number for t, plug it in, and that's a point on this line that they all have in common. So that's how we deal with consistent dependent systems. Now we have one more elimination problem. You notice that once again, our x's or our y's don't line up for elimination, so I'm going to have you pause the video and try this one. Multiply the lines by something so that you can get either the x's to eliminate or the y's to eliminate, and then come back and check your answer when you're done. Let's see how you did. Now, you may have multiplied by different numbers than me. That's totally fine. But either way, when you add these together and eliminate, you should get a false statement. 0 does not equal negative 18. That is false. That does not work. Now, anytime we get a false statement, that tells us right away that this is an inconsistent system. And if you remember from the first video, that means there are no solutions to this system. Because we got a false statement, this is inconsistent. So we can simply write no solution, and we're done. So that is all the examples we're going to do with elimination. We got an example of each system: consistent independent, consistent dependent, and inconsistent. And hopefully you're starting to feel a little more confident with elimination. We're going to do a lot with elimination this chapter. In the next video, we're going to start to move into, I almost forgot to show you. Really quickly, let's come back to our no solution and show you what this looks like. So basically, the no solution means that these lines have no points in common. So let's look at what that looks like graphically. There we are. They're parallel lines. So because they're parallel lines, they will never intersect or cross each other. That's why they don't have any points in common, and that's why it's no solution. So that should help you visualize each of these answers a little bit better. Consistent independent is when they have 1 point in common, 1 point where they intersect. Consistent dependent is when the lines overlap each other, and so these are all the points they have in common, infinitely many. And inconsistent system is when they're parallel lines, they never intersect, so there is no solution. So that's everything we need to do with elimination. Now in the next video, we're going to start to move into nonlinear systems, meaning we're looking at curves now instead of straight lines.